Well, hi all, it's Rob here again. Welcome to part 5 of my heating design course, free online course for everybody, so it'll be here forever. You can just download it or play it whenever you like and reference it at any point you want to do in the future, so hopefully you'll all get involved in that. We are talking today about a final index circuit calculation. In the previous slide, if you remember, I'll come on to that in a second, but in a previous slide, if you remember, I described an index circuit as long as the flow can get over the highest resistance, when in this case it's just the tallest bit of pipe work here with no other valves or anything like that in it. As long as it comes out of that, it will definitely come out of all of the rest of them, as we can see there, and that kind of makes logical sense because there's less height and less resistance that this has to get over. That's exactly that. Let's just use that as the example. But what we need to do is put that into mathematics, into a system like this. Now, this is a typical one-bedroom house. You can see I've drawn this drawing out in isometric. So there's an upstairs wall there, another upstairs wall there. You can imagine there's some imaginary stairs in here somewhere on this landing. But it's a room by room, and you can see so this bedroom here, bedroom 1, that's that rad 4. Landing is rad 5. The lounge you can see here is these 2 radiators here, so that's rad 2 and 3 in this system. So it's a basic 6 radiator system. And what I want to do, we've done a heat loss calculation room by room, and we've come out that this little property is 4.1 kilowatt, probably a bit higher. It should be around about 3 kilowatt really for a little small house like this. But anyway, that's it. I've done it on purpose because I want to play around with what the index circuit is. So I've made this lounge quite high to just play around with this and sort of like go through this discussion. But what we're going to do is, you can see from here, we've had a client that's given us a call, and they want to upgrade to a heat pump. And your job is to go round to this property and look at this property and say, right, okay, is the existing pipework ready? So do I need to upgrade any pipework? And I'm going to throw some curveballs into this as we go, and we'll calculate them out just to see if it's going to work, and we'll do the calculations for it. So it's quite a longish tutorial. It takes as long as it takes, but I'll edit out all the bits that we don't really need as we go along. So anyway, we have a few things that we need to understand when we're doing index circuit calculations, and this is obviously we're just trying to get over the highest resistance. There's a few things that we need to work out, obviously, as we just said, and they are sections and circuits. So if we go to the next slide and we can look at circuits, you can see it's the same drawing. It's the same drawing here, all right, but this is labeling circuit. So you can see we've got a circuit running from the main primary flow and return here, and it runs out, it tees off there, and it runs out that way, out to that rad 4, but it doesn't go any further. So that's just circuit 1. We've then got another circuit, which is circuit 2, and it runs straight through and it feeds rad 5 and 6. And then we've got another circuit, which is circuit 3, which runs a primary flow to return as well, and across to this point, and then it tees off there and it goes down to rads 1, 2 and 3. So we've got to calculate all of those resistances in those 3 circuits and find out which one is the index circuit and where the index circuit is. On top of the fact of labelling circuits, you've got another thing that we need to do, which is recognise sections. And this is sections that we need to calculate the resistance to flow through. So we look at sections and we give these IDs, we do A, B, C, D, E, F, G, whatever it is that you want to do. I mean, you can do it the other way around. You can have circuits A, B, C, D, and if you want, and then sections as one. It's entirely up to you. It's only about labelling. But you can see again, so we've got circuit 1. So this circuit 1 here, how many sections do we actually have on it? So we look at the sections. You can see we've got one section there because it's your primary section, and another one there. So there's 2 sections that we need to calculate. So for circuit 2, we've got 1, 2, 3, 4 sections that we've got to calculate. And for circuit 3, we've got 1, 2, 3, 4, 5 sections that we've got to calculate out. And the only reason that we have to do this 3 times is because this is a section that is common to all 3 sections. This section here, section B, is just common to circuits 2 and 3, as you can see there. But nothing else is common to anything else. All you've got is that one there, that section C, that there is common to both section C and section D. So that is carrying all of the energy for rad 5 and rad 6. But when you get down to this point here, this right hand side of this radiator, that is only taking or need to carry the energy for section D, and that's it. So it's very, very simple, and you can paste this out whenever you go into a project. So this is quite an easy one to do, and normally should take you, if you're on site, should normally take you about 15 to 20 minutes to actually calculate the index circuit of whichever one it is that is there. But as I say, a few things to do. So we know now, going back to this previous page, that we've got 3 circuits. So what I suggest people do is you draw out just a little chart like this of your circuits, so A, B and C, or circuits 1, 2 and 3, whatever it is that you want to do. And then we have a few things in here where what we do is we add them up as we go along, and then we put the totals in the bottom, and that's going to be, whichever one's the highest is going to be your index circuit, and that's how you would size your pump to what that total pressure loss is, or resistance to flow is, across that one circuit, because we know that whatever the highest one is, let's just say it's B for argument's sake, if it was B, would that circuit then, if that was the highest circuit, you know if you can get over the pressure loss of that, it will get over the pressure loss of those, as we described in our previous triangle type chart, because this has got a higher pressure loss, so as long as it gets over the high pressure loss, it will get over these other two. So that is your index circuit. So let's just go back to the main page here and look at this. Now you can see this is a room by room heat loss calculation, and I've put all of the, like bedroom 1 needs 323.87 watts. Well, we'd probably just round that up to 324 watts, and the same landing 150 watts we do, that we'd put in as 500 watts, that sort of thing. So we'll play around with this as we go, but what I want to do is talk you through how you recognize bits of pipe work. Obviously we now know circuits and sections, that sort of thing. We need to know the pipe sizes that are in there, and certain bits that are common, as we just spoke about there, and calculate them out. So when we're doing an index circuit, if we calculate out that first section there, or the first section of circuit 1, we'll do circuit 1 first of all, or circuit A, as we said on my sheet, so it doesn't matter. If we pull up the calculator and we have a little look, so we use the we're going to need that one, and we're going to need that one. So if I just pull that side by side there, so we've got the two up. So we've got the app and we've got a calculator that we can use, and you'll need both of those as you're doing these longhand. So let's have a look at this first of all. So what is common? Well, we know that this primary circuit here is common, and we've got 22 millimeter installed at the moment. As we this is general that we can see in a lot of properties. You'll generally see there's 22 millimeter installed or 28 millimeter installed, and it'll run down, or 22 will run all the way down. Then we might be 15 mil drops there, or something along those lines. But I'm going to throw some curveballs in, and we'll kind of add them up as we go. So let's go on to our calculator, and we know what our total heat loss is. It's 4.1 kilowatts. So if we go to our app, remember what we said that we have to do with the app first of all. We've got to go in and we've got to set the flow temperature. So we're putting in a heat pump, and we want to get this heat pump as efficient as we possibly can. So let's try, I don't know, let's just say a nice flow temperature figure of say 40 degrees. So first thing we've got to do is go onto our temperature setting, make sure that we're sitting, our fluid is on water. As I say, with this you can actually change it, and you can have glycols and all sorts of things to go into it. But let's stick with water, because I like to work to VDI 2035 and use chemical free and demineralized water, but we'll talk about that on another tutorial. So we know we've got to change that temperature to 40 degrees, or whatever your design flow temperature is. So make sure you do that, because as we know, that has now changed the specific heat capacity of that water down at the bottom for our mass flow calculation. So we go to then calculator, and we say, right, we go on to the power delta T calculator. We want flow, so remember we click on the left hand side to get flow, and we need 4.1 kilowatts. But we're now doing it, because it's a low temperature system, we're now doing it at DT5 as we discussed. So we click that, and we can see that we need 0.19, well basically 0.2 litres per second. That's going to be our flow rate that we're going to need right the way through there. So again, now how do we look at the pipe work sizing? So we go to pipes. We can see it's on table X copper, as we've said there. again, we can change that to whatever it is that we want, and we can see that it says 22mm pipe. Now that's really good because it's saying it's got 0.62 meters per second. We could make an engineering decision, not that I see much 18mm table X copper, but we could use 18mm table X copper because our target velocity is 1 meter per second, as we said, and we're 0.94 there. I know this is a little bit high, but we'll talk about the lengths of this in a second, as we did before in our previous index circuit. But we've got 22mm installed, so this is the magic figure that we want. Okay, now you can see that I've written on here that this is 1.5 meters long. So all we've got to do is go onto our calculator, and we've got to say for our primary circuit coming through there, we've got to say, well, okay, it's 246.8 pascals for 1 meter, but we want 1.5. So if we say 246, don't really need the 0.8, but we could do it to 247 really if that was the case. But let's be really accurate. Times 1.5 meters equals 370.2. Now, is that correct? Well, no, it's not, because we've got a flow and we've got a return. So we've got to double it up. So we've got to go to 3 meters. So we could just go now answer times 2. Okay, so we've got 740. So there's 740 pascals in that primary flow there. 740 pascals. Now, do you remember we said that we would have to add on for fittings, any pressure drop for fittings? Well, this is the section that we're doing, is just this one section. We haven't changed direction yet. So we have no changes of direction at this point. So you can see there is no change of direction. So that is your figure, 740.4. We'll just call it 740. And then in the next slide, I'll show you where we start to input that data. Okay, so we had 740 on our circuit A that we can put in. But there's something that we need to discuss first of all. And that is, we've said what is common to both circuits A, B and C, or circuits 1, 2 and 3, which however you label it, and that is with the primary flow and return. We know that that is common to everything, but you can see I've given a little hint and a clue here to what is going on as well. There is also a resistance to flow within the heat pump itself, so within the heat exchanger of the heat pump itself. And we want to know what that is. Now, these can change, and you need to get, depending on the size of the heat pump and all the rest of it that you've got, but you need to look in the manufacturer's instructions or speak to the manufacturer's technical departments and find out what the resistance is through the heat pump at delta T5. That is a very, very important thing. So what I'm just going to do for this particular example, I'm just going to say we've got 5 kPa running through it. Now, I know that might sound a bit low, it might be a bit higher than that or whatever it is, but I'll just pick 5K. So that's 5,000 pascals on this one. But we know it's common to every single circuit. So if we double click on this and we say that has got 5,000 pascals, that's 5,000 pascals there. We also know that this one has also got 5,000 pascals. And then we also know this one has also got 5,000 pascals. But we now know as well that for this next bit, we've also got 740 pascals for section A. So we say 740 in there, but that's common to all of 3 of these. So again, we've got 740 there. And again, we have 740 there. Okay, so that's our first part that we've done. So we go back to our next section, which is that section going out there. And I'm going to play around with this now, and we're going to see what we can do. So let's say we've walked into this property. Let's go back to the previous slide. So we've walked into this property. We started to walk around. When we were doing our room-by-room heat loss calculation, we realised that bedroom 1, it had a wooden floor, and it was an engineered wooden floor that was in there. All the pipework is under the floor, and it's hidden, and there's not a lot we can do about it. It would cost quite a lot of money to take that floor up, and they'd probably end up having to renew the whole floor. Now, not necessarily the end of the world, but it's still a cost concern. We've looked at the pipe tails coming out of the floor here, and we've actually realised that it's 8mm table Y copper. So we have to now start thinking about whether this is still going to work on a DT5 low temperature heat pump system. Radiator sizing will come on to a different point. We're only interested in the index circuit calculation at the moment. As I say, there's no resistance through the radiators. So we have to calculate that out. So if we bring our calculator up again, bring both of these up again, and we now say that we go back to our calculator, what we do need to do, because we know that this is 8mm copper that's running out from this point here, from that T-piece there, T1 if you want to call it that, from that point there, we know it's 8mm copper, but it's table Y from that because it's soft copper. So the first thing we need to do is change your pipe selection to table Y, because there's some slight difference of resistances on it. So now we go back to our calculator, but we can see that our radiator size there, so the only energy that's coming down this pipework here is for that one radiator. So it is 323.87 watts. So it's 324 watts at the end of the day. That's the kind of easy way to kind of round this up. That's what we want. But what does our flow ohms triangle state? It says we need it in kilowatts. So when we enter this in, our power, we put in 0.324 watts at DT5. And we can see that what we need there is 0.0156, so 0.016 litres per second is what we need travelling from that T-piece there all the way down to this radiator. So let's have a look at it. So what have we got? If we go down to, if we click done there and we go down to pipes, and we've got table Y copper. Well, look at 8mm. Let's just discuss it. Yeah, look at our pascals per metre. Our pressure drop is 700. As you can see right there, but look at our pressure drop across it. It's only 0.5 metre per second, so it's really quite low flow rate through there, even though there's some fairly high resistance through it. But let's have a look. So we've got our resistance there at 700 pascals times, we've got 3.5 meters of length there between there, but because we've got a flow and return, we double it up, so that's 7. So we literally come over to here now and we say 700 pascals times 7. But how many changes of direction do we have now for our fittings? Remember we said 10% per change of direction. Well, we've got a change there as it tees and it goes left. That's one change of direction. We've got another change of direction there, and we've got another change of direction back up into the radiator. So that will be 3 changes of direction. So it'd be 700 times 7. That gives us 4,900 pascals. But then we've got to add 30%. So we times that by 1.3. And that gives us 6,370 pascals. How easy is that? So if I go to the next slide and we add on here 6,370, because we know that's what that pressure loss is to that radiator. Now, we don't now need to do anything here, or we don't need to put this 6,370 on circuit B or circuit C, because we know on this section here that is that one circuit there complete, and it's got the 2 sections, 1 section there, 2 sections there. And as you can see, what we've done is 1 section there and 2 sections there. So this now is circuit A. What we can do now is we can bring up our calculator and we can say that we had our hex resistance, so our heat exchanger resistance of 5,000. So we say 5,000 pascals plus 740 plus 6,370 equals, and we've got 12,110. And that is circuit A completed. So that one circuit is 12.1 kPa. And remember, one of the smallest pumps we can get is 50 kPa or 40 kPa. You'll find that a lot of heat pumps actually will have a much higher kPa rating within the heat pump itself, and it's more like going to be something like a 100 kPa, or certainly an 80 kPa or something along those lines. I've actually seen them at 120 kPa, which is 12 meters of head, or 120,000 pascals. And this is something that we need to get our heads around and understand why people are oversizing pumps way too much. Now that is, we've proven now that with a heat loss of that bedroom of 380 watts, I think it was, something along those lines. Let's have a quick look and make sure that we're right. Yeah, sorry, 323 watts or 324 watts there. We know that existing 8mm pipework doesn't need changing. And that's the point we really want to make when we're doing this. There is a caveat which we'll throw in towards the end of this tutorial video, but we'll go through that. So all you need to do is literally, and I'll list these out very clearly on the next slide. Okay, so we saw on the previous slides that we have different sections within our circuits. We know we've got circuit 1 here, or circuit A here, circuit B or circuit 2 and circuit 3 here, and then we're using our sections, we label them either in alphabetical order or in numerical order. It makes no difference. There's two things you've got to do when you're measuring a different section. So you can see from that T piece there, that length of pipework between there and the right hand side of that radiator. If your flow was coming from the other way, it would be to the left hand side of the radiator, but you're taking the full length of those and then multiplying it. So that whole section between that T piece and there, you see it's 4.3 meters. We actually turn that around and that would be 8.6 meters going right the way through. So there's three major points that you need to remember when doing it. So we know we've calculated out circuit A and we've got to 12 kPa, 12,000 pascals. We go to circuit B, and remember we've got to find out which is the common, which we've already done. So we've done the primary circuit already. We do this little section here. So what we need to do is say, how much energy is that section there? What is it taking? Well, let's bring up the calculator and let's have a look. It's transporting all the energy to both circuits 2, or circuit B, and circuit C. So circuit 2 to circuit 3. All of that energy. So how do we find out how much energy that is? Well, it's really quite simple. We had a heat loss of 4.1 kilowatts in total. So all we need to do is come down to here and we can say 4.1 minus this one here, which is 324 watts. So we say minus 0.324, and that equals, so we've got 3.77, so 3.78 kilowatts. 3.78 kilowatts is all we need for that. So for that section there, we go back into our if we say we've now got 22mm copper there as well, for argument's sake, because that's part of that main primary. So it's 22mm copper. We now need to change it back to table X copper, because that's the type. Very important that you do this. Go back to our calculator. We're on the flow, so we're working out what we need, but we've now got 3.78 kilowatts. As we can see, that's our revised energy of what that section is carrying us. All you need to know is whatever a section of pipework is carrying or transporting, you just need to know what the pressure loss is of that and the kilowatt rating of what it's taking. And that is on any type of system, whether it's, as we've said before, 6 radiators here or 600 radiators or 6,000 radiators. That's all you need to know. Do a section at a time. Very important. So we just go into our calculator and we say we've got 3.78. Oh, sorry, that's not correct. That's my fault. 3.78 kilowatts, which we've agreed on at delta T5, and we're all good. So we now click on pipes, and we got the same again. We've got 214 pascals at half a metre, or nearly 0.6 metres per second. So that's pretty good. We're happy with that. But what have we got now? We've got 214 pascals, but we've only got half a metre. We've only got half a metre of that. There's a couple of things I want to show you. I'm going to show you quickly on another slide, because I want to find out how many changes of direction are there. And it's very important that you kind of understand this, because there's something going on just here I just want to need, and it might be the way I've just drawn it, but I just want to just zoom into this and show you this in a second. But if we've got 214, we've actually got to halve that because there's only half a metre of run. So that then would become 107, wouldn't it? So 214 divided by 2 is 107. I mean, none of us need a calculator for that, hopefully. So we have 107. So let's just put the 107 in now while we've got it here. And then I'll show you the next bit on the next slide. I've zoomed into this slide now and you can see there's your primary flow and return coming up. We've done this section already here, but we're trying to work out how many changes of direction that we've got in this small section here of half a metre in length. Well, you can see that we've actually got a change of direction there. So we've got 2 T-pieces, but there are also 2 elbows in the end of those T-pieces where it turns 90 degrees and comes this way because it's drawn in isometric format. So we actually have one change of direction there and then another one just there. We haven't gone past that section there, so there's 2 changes of direction, and that would mean 20%. So if we bring up our calculator and we look at our pressure loss that we knew, which was 107 pascals, this is a very, very small amount of pressure loss here, but we'll say 107 times two changes of direction, so it would be 1.2 equals, and there we go. So we've got 128.4 pascals, and we'll come on to the next slide and work out where we need to put those figures into. Okay, so we're back on the page now of our chart, and we're in circuit B, or 2, or whatever you want to call it. As I say, I shall stop saying that. We'll just call it A, B, and C. Everyone knows what we're doing by now. And we had 128.4. We'll just round it up. So we've got 128 pascals that we have to add on to that. Now, the thing is that we realised earlier is that that section in B was, I'll just quickly go back to that page, that section in B, or B section there, it's common to both circuits 2 and 3. So it's really important that what we do is put it in both sections. So we put 128 in section C as well, and that is there. And now you can see pretty much, I'm pretty sure most people now that are watching this are understanding it's so easy to calculate an index circuit because you just keep adding these on and adding these on. But we'll carry on for another couple, and then what I'll do is I'll just complete all the ends and get all the total figures up and then show you, and we'll discuss the end result. So we'll just do one more calculation so we're up to speed with this, and then we'll move forward. So next section, in section B, we'll go on to that calculation. Okay, so we're on section B now, or circuit 2, and we've got section C here that we need to calculate out. We've done B, and we're moving on to this. So we're doing this one circuit going out here. So what we need to do, remember, we said look at the size of the pipework, and we want to say how much energy is that pipework carrying, and where's it going to. So basically, we know that section of pipework there is carrying all the energy for rad 5 and for rad 6. So, and we can see that our total that its energy it's carrying is for the landing at 149.86 and the bathroom at 499.25. So if we bring up the calculator again, let's get rid of that, and we say we've got, so we round that up to 150 plus our bathroom is at 500, so we know it's going to be 650. So we've got 650 watts that bit of pipe is carrying. So let's just say now we've got, what should we say? We'll say we've got 15mm pipe. It's been reduced down in size from that 22mm there on section B, and it's reduced down to 15mm to feed these 2 radiators, right, as we stand. So we've got 650 watts that we need to find out whether 15mm pipe work will be good enough. So we know it's table X. So again, we go back to our calculator and we punch in there 650 watts. And remember, it's in kilowatts, so it's got to be 0.65 would be 650 watts at DT5. Click done. We need 0.0313 litres per second. Click onto pipes. Check we're on table X. We've got 15mm in there. and that's only giving us 0.22 litres per second at DT5. Now, I don't know if anybody's done the great Kimbo's course, but he will teach you that 0.2 meters per second is what is called Stokes' law, and we'll come on to some of those laws and the rules and regulations, if you like, as we move further into this design course, and so it will go on for as long as you guys want it, and the more you want, the more we can do, I guess. But 0.2 meters per second actually means that dirt will not move through the pipework. It becomes sedentary, and this is when we size things like low loss headers for hydronic separation and that sort of thing. I mean, I tend to size them around 0.1, but that's just because that's me. But 0.2, so we're just over that at 0.22 meters per second. So the velocity has gone right down. So we know that pipework will work, but there is a possibility of that pipework getting corrosion within the pipework, if we're not careful, even though we're running at DT5, which is 4 times the flow rate of everything, of a DT20 system. But you can see we've got 65.9 pascals. So 65.9 pascals. So we'll have a look at this now. This section, it's 4.3 meters, but we've got a flow and return. So that becomes 8.6. So we have to say 65.9, let's just call it 66. That's perfectly fine. So we've got 66 times 8.6. 66 times 8.6, that gives us a pressure drop of 567.6 pascals over that length of copper there, because we worked out that it's the bathroom and the landing that we need to calculate through. How many changes of direction have we got? Well, there's not a change of direction there because it's coming straight the way through those T-pieces. So there's no change of direction there. There's just one going up into the rads, and that's it. So we literally then just have to add 10%. So we've got that, and we just times that by 0.1. And there we go. And there's our pressure drop for section C. And that is 624.36. Not worth putting that. So 624 is absolutely perfectly fine. And we'll put that in onto the next slide. So you can see this on circuit B here. We had 600, can't remember now what it was. We had 624 watts. Pascals. 624 pascals. I think that's probably enough to teach you how to do these index circuits, but what I'll do is I'll just privately now just calculate all the rest out quickly, and then I'll show you on the next slide of what our totals are, and we can discuss our pressure drop. Right, so we're now back at our next point here. I've completed all of the index circuit calculations, and the bits that I'd missed out were, so this section of pipework here was just 15 millimeter pipework, which gave us quite a high pressure loss because it was carrying both the energy for the bathroom and the landing. And then this one I dropped it down, I think, to just because it's taking the bathroom. I dropped that down in size. I think it was to 10 millimeter. Just to try it. You can try it with different sizes of pipework, and you can play around with it in your own house and stuff. The point is that you get the understanding that you just do one section at a time. The questions you need to ask are, how much energy is that section carrying? Whether it's for just that one radiator or for multiple radiators downstream or emitters downstream, how much energy is it carrying? How many changes of direction has it got? And what size of pipework it is. That's all you need to know to do index circuit calculations, and to just be methodical and work through them section by section, and away you go. I put down here from this T-piece, I put 22 millimeter down to the edge of that radiator because we've got quite a high heat loss here. But there was 22 millimeters there, or we could say that it wasn't there, and that bit of floor would have known, or the bit of ceiling might have been needed to taken down there and join into that primary flow and return to drop down. But in this case, it was there, we're saying. But then from there, I dropped it down to 15 millimeter all the way down to this end up section. So what I've ended up, and might sound quite surprising. Now, I'm sure most of you have probably either guessed now that it's either, hopefully you've worked out, but it's either circuit A, circuit 1, whatever it is, circuit A, circuit B, or circuit C. Now, as it turns out, it worked out to be circuit C. And you can see that we, even then, with a delta T5 system on an existing pipework scenario, the index circuit is 13,556 pascals. Now, that's not quite it, and we're going to need to do a little bit more. But the bottom line is that, a 20 kPa pump, if you could get hold of one, a 20,000 pascals pump would be perfectly suitable at DT5 for that particular type of system. But we know that from our when we're sizing the pump, we know that we had a total heat loss of 4.1 kilowatts, and we need to work out what that would equate to in terms of flow rate. So again, we go to our mass flow calculator, we put in our 4.1 at that point there at DT5, and we can see that we need to find a pump that is giving us 0.2 litres per second. Now, you might decide that if you've got a low temperature system and you've also got a hot water cylinder in there, you then need to look at what the pressure loss is through the heat exchanger of the hot water cylinder, and find out what the kilowatt rating is of the hot water cylinder, and you might need to size for that if that is more important to you for sizing for hot water. As we've discussed on many forums now, oversizing of heat pumps, a lot of them now we do size for hot water more than anything else, and it doesn't matter too much if we oversize, around 20% if we oversize, as long as you can get lots and lots of system water volume in. So the larger the radiators you can fit into a property, the better it is. And if you have to go down the route of buffers or volumizers, then we'll talk about that on another tutorial video, or you can watch some of the podcasts that are out there right now where we have discussed this exact issue. So a couple of things we need to discuss now. We know that we've got an index circuit of the pipework only and the heat pump of 13.5 or nearly 13.6 kPa. That's a rating going across the whole too. Excuse me while I get some water. But that might not be the index circuit. We might find that the index circuit is a valve. So you need to find out what the kPa rating is of any motorized valves that are within the system, any radiator valves that are in the system that you have. And I'm just going to do a quick demo here looking at this rate. So if we take that last radiator there, which was the last section of pipework going to the last radiator, let me just push that down a second and I'll show you what I mean. So the last calculation of 1304 pascals was in circuit C, and it was this bit here. What I did, there was like 2,473 watts of energy needed in that lounge, and I made it, that's overkill, so it's purely an example, and I just made both of those radiators exactly the same size. So when I calculated that section of what energies that is carrying, I just halved that amount. Okay, so half that amount running through 15mm pipework, and obviously the pressure loss is only 1304 pascals. So that's it. But what if with different types of radiator valves that are on these circuits? And if we need the 0.059 litres per second, which is up here, and that comes back from our calculator, that won't change, so that will still be up the same there from our ohms triangle that we've done. Let's just go to this, because this tool does, and this will be for another tutorial video, but it'll start to help you understand some kPa ratings of valves, and we'll talk about kPa ratings and kV ratings on either the next tutorial or the one after that. I'm not too sure yet as we move forward. It's all quite organic, this, and I'm sort of winging it as we go along, but I quite like that. So let's have a look at this. So if we go now back onto, because this is a dynamic app, if we click down the bottom here onto home, you'll see what happens. We can actually go now to radiator valves. So we click on radiator valves, and we can choose, you can see what's happened dynamically. Our flow rate has come right the way through to this point here. This is quite interesting to look at. Now, there's certain types of valves. As you can see what we've got here at the moment, we've got eclipse valves, and you've got lots of different types of valves. This is just the pressure independent valves that IMI Hydronics do. These are the eclipse valves. Now, I'd only recommend eclipse valves for sort of higher temperature systems, certainly sort of 50 degrees or higher, that sort of thing, and slightly wider delta T's if possible, because you can see that what it's asking for that particular 0.059 litres per second, it's stating an eclipse 300 valve. But look at the delta P, so the pressure, the difference in pressure across that valve in kPa. Now we knew that we had 13.4 or something like that kPa on our index circuit. But look what it's saying here. It's saying that dP minimum over that. So we actually need, that is going to be your index circuit. That valve is going to be your index circuit. So it's very, very important to understand that we'd have to find out what the pressure losses are over any valves that are on the circuit. So I really hope you enjoyed this tutorial video. As I said before, please give it the thumbs up and subscribe if you can. Maybe hit the bell icon and you'll get notified if when the next one comes out, because there's going to be quite a few now, and I'm going to try and sort of up this and speed up the process a little bit if I can make some time. I am going to set this GoFundMe page up. I've had plenty of private messages saying that people would be very happy to put a couple of pence in, which would be very, very welcome. So thank you for that, and thanks for all the support that everybody's given so far. It's been well, quite overwhelming actually. I wasn't surprised. I'm quite surprised that I've got so much, but it's very good. So I thank you all very, very, very much, and I will see you on the very next video. Many thanks. Goodbye.